When a matrix transforms space, most vectors get pushed off in new directions, rotated, stretched, scattered across the plane. But hidden inside every matrix are a handful of special directions that refuse to turn. The matrix can scale these vectors, flip them, even crush them to zero. But it cannot rotate them off their line. Right? These are eigenvectors, and their scale factors are eigenvalues. Find them, and you unlock the matrix's deepest structure. The entire idea fits in one equation, a times x equals lambda times x. Let's break down what each piece means. A is the matrix, right? It represents the transformation. X is a non-zero vector, the eigenvector, and lambda is a scalar, the eigenvalue. This equation says something powerful. When A acts on X, the output lands back on the same line as X, just scaled by the factor lambda. X is the eigenvector. It's the direction that survives the transformation. So lambda is the eigenvalue. It tells you how much that direction gets scaled. Now let's look at what different values of lambda mean. If lambda is greater than 1, the eigenvector gets stretched. It grows longer. If lambda is between 0 and 1, the eigenvector gets compressed. It shrinks. If lambda is negative, the vector flips to the opposite direction. And if lambda equals 0, the vector gets sent to the origin. It's annihilated entirely. A projection matrix makes this concrete. Take P, a matrix that projects three-dimensional space onto a plane through the origin. First case, a vector lying in the plane. Projecting it changes nothing. P times x equals x, which is 1 times x. Lambda equals 1. That's an eigenvector. Second case, a vector perpendicular to the plane. The projection crushes it to the origin. P times x equals the 0 vector, which is 0 times x. Lambda equals 0. This is also an eigenvector. And this vector lives in the null space of P. The null space is the set of all vectors that a matrix sends to 0. Third case, a vector at an oblique angle, partly in the plane, partly perpendicular. Its projection lands in the plane, but it points in a different direction than the original vector. The output is not a scalar multiple of the input. This vector is not an eigenvector. Only the in-plane and the perpendicular directions qualify as eigenvectors. Here's a different example. The matrix A has entries 0, 1 in the first row, and 1, 0 in the second row. In this matrix, swaps the two components of any vector it acts on. Let's test the vector 1, 1. A times 1, 1 gives 1, 1. Swapping identical components changes nothing. So lambda equals 1, and 1, 1 is an eigenvector. Now test the vector, negative 1, 1. Times negative 1, 1 gives 1, negative 1. Let's check negative 1 times the vector. Negative 1, 1 equals 1, negative 1. That matches. So lambda equals negative 1. Here's a surprise. Every entry of A is non-negative, yet one eigenvalue is negative. Also notice that these two eigenvectors, 1, 1 and negative 1, 1, are perpendicular to each other. Their dot product is 0. Right? This is a consequence of A being a symmetric matrix. We've seen the clean cases. Now let's look at the edge cases. Lambda equals 0 is a valid eigenvalue, and this is a common source of confusion. If lambda equals 0, then A times x equals 0 times x, which equals the 0 vector. So x is a non-zero vector that A sends to 0. Right? By definition, that means x is in the null space of A. Here's the key consequence. If any eigenvalue is 0, the matrix is singular. Like its determinant is 0, and it crushes space by at least one dimension. Picture a rank 1 matrix collapsing the entire plane onto a single line. Vectors along the output line are eigenvectors with a non-zero eigenvalue. They survive the transformation and just get scaled. But vectors in the null space direction get crushed all the way to the origin. These are eigenvectors with lambda equals 0. One final important point, the 0 vector itself is never an eigenvector. We always require x to be non-zero. The equation A times the 0 vector equals 0 is trivially true for any matrix, so it tells us nothing. What about pure rotation? Take a 90-degree counterclockwise rotation in 2 dimensions. The rotation matrix is 0, -1 in the first row, and 1, 0 in the second row. Apply this to any real vector, and that vector moves to a completely new direction. No real line survives the transformation. Let's find the eigenvalues. We compute the determinant of A minus lambda y, which gives us negative lambda times negative lambda, minus 1 times negative 1. Let's simplify to lambda squared plus 1 equals 0. The solutions are lambda equals I and lambda equals negative I are both complex numbers. Since the eigenvalues are complex, no real eigenvector exists. There is no real direction that stays on its own line after a 90-degree rotation. This gives us an important general rule. Real eigenvalues mean some directions survive the transformation. Complex eigenvalues mean the matrix rotates everything off course. No real direction is preserved. Now for a pair of facts that tie eigenvalues directly to the matrix itself. First, the sum of all eigenvalues equals the trace, which is the sum of the diagonal entries. Second, the product of all eigenvalues equals the determinant. Let's verify both properties with our permutation matrix. The permutation matrix has entries 0, 1, 1, 0. Its diagonal entries are 0 and 0, so the trace is 0 plus 0, which equals 0. The eigenvalues are 1 and -1. Their sum is 1 plus -1, which equals 0. That matches the trace. Check. Now the determinant. 0 times 0 minus 1 times 1 equals -1. On the product of eigenvalues, 1 times -1 equals -1. That matches the determinant. Check. Now let's verify with the 3x3 projection matrix, which has eigenvalues 1, 1, and 0. The sum of eigenvalues is 1 plus 1 plus 0, which equals 2. This matches the trace of 2. Check. The product of eigenvalues is 1 times 0, which equals 0. This matches the determinant of 0. Check. A 0 determinant confirms that the projection matrix is singular, and this makes sense. A 0 eigenvalue always forces a 0 determinant because any product containing a 0 factor is itself 0. These concepts aren't just classroom exercises. Eigenvalues and eigenvectors power some of the most important algorithms in science and engineering. First, consider Google's PageRank algorithm. It computes the dominant eigenvector of the web's link matrix. Each component of that eigenvector assigns an important score to a web page, and the direction the matrix agrees with most, that is the eigenvector with the largest eigenvalue, determines search rankings. Right? So pages with higher eigenvector components rank higher. Second, in structural engineering, the eigenvectors of a stiffness matrix describe the natural vibration modes of a bridge or building. Mode 1 might be a single smooth arch shape, while mode 2 might be an S-curve. The corresponding eigenvalues give the squared natural frequencies of these vibration modes. Third, in data science, principal component analysis, or PCA, finds the eigenvectors of a covariance matrix. These eigenvectors point in the directions of maximum variance, which are the axes that capture the most information in a data set. The eigenvector with the largest eigenvalue points along the direction of greatest spread. From search engines to bridges to machine learning, eigenvectors reveal hidden structure in the systems we study. Every matrix transforms space. Most vectors get scrambled, rotated, and rescaled beyond recognition, but the eigenvectors hold their line. The eigenvalues tell you exactly how each surviving direction behaves, stretched when lambda exceeds 1, compressed when lambda falls between 0 and 1, flipped when lambda is negative, and annihilated when lambda equals 0. In our example, lambda 1 equals 2. The eigenvector gets stretched to twice its length. lambda 2 equals negative 1/2. The eigenvector gets flipped and compressed, and their sum 2 plus negative 1/2 equals 1.5. And that gives us the trace of the matrix. Their product 2 times negative 1/2 equals negative 1, and that gives us the determinant. Every matrix, no matter how large or complicated, has these hidden directions. Directions it can only scale, never rotate. Find them, and the matrix reveals everything, what it preserves, what it destroys, and how it reshapes the space around it.